Hello everyone. Today we will introduce our Wang for all vectorized solution to merge sorted key-value arrays. Let's first look at some examples. Sparse linear algebra. That is, we are going to perform additions, multiplications, or element-wise multiplications between sparse vectors, matrices, and tensors. Sparse objects are usually encoded as sorted key-value arrays, where keys are the indices for the non-zero elements. Keys can be tuples for matrices and tensors, and in that case, tuples are sorted according to their lexicographic order. Sparse operations like element-wise multiplications or additions can be encoded as merge operations on those sorted key-value arrays. Sparse linear algebra is not the only place where you can find merge-style operations. In database, you have various join or sorted set operations. In graph algorithms, you manipulate adjacency list using merge-style operations. In sorting, like merge sort or team sort, you recursively merge subarrays. And in range match, like piecewise function interpolation or COO/CSR format transformation, you also have merge-style operations. Vectorization is an important technique to improve the performance, but it is hard for MSO because both of its two input arrays are indexed by keys. Index matching is a missing feature for the current SIMD instruction set, so in most cases, MSO has to be implemented in sequential code. Why doesn't such important operation have specialized SIMD instruction support? Well, there are reasons. So in the rest of this talk, we will first discuss the fundamental challenges of MSO that prevent it from vectorization. Then we will present our solution to this problem. That include an uniform abstraction, 4 new SIMD instructions, and the circuit design. The first challenge is that we cannot provide infinite types of SIMD instructions, and the complex MSO cannot be reduced to simple MSO. MSO used in applications is diverse. They have pattern diversity or rule of matching, such as finding union, intersection, sorting, or range match. They also have data type diversity, such as key and values to be data structure of any type. Complex MSO whose keys and values to be data structures cannot be reduced to simple MSO whose keys and values to be primitive types. Therefore, providing a finite set of simple MSO such as sparse vector additions cannot be used to implement an infinite set of complex MSO. This is different from element-wise operations. We take a different approach in this work. We introduce a uniform way to represent MSO, including both the simple ones and the complex ones. And then we introduce 4 new low-level SIMD primitives to implement all of them. Another challenge is that, as in prior work, we need to implement a square comparator array, whose hardware cost grows quadratically with the SIMD width, while the performance we get grows only linearly. We solve this problem by providing a circuit design that reduces the cost from V square to V log V. Now, let's get into the detail of our design. The first part is an abstract machine serving as the uniform representation of MSO. The second part is the 4 SIMD primitive, and the third part is the circuit design. Let's first look at the set union example. We will introduce a pair of aligned array as intermediate result by inserting zeros for the unmatched pairs. Starting from this step, the merge operation is transformed to an element-wise operation. But how to generate the operand string? It can be generated using a pair of controlled FIFOs. A sequence of commands will instruct the FIFOs to insert zeros at proper positions. But how to generate the commands? The commands can be generated from the input arrays like following. First, we merge sort the 2 input arrays and record for each element where it comes from, A or B. We call this extended merge sort. Then, for each element, we extract 5-bit matching information from its left and right neighborhood. This can be also considered as a sliding window. Finally, we use a lookup table to determine the commands for each element, using the 5-bit information as indexes. By changing the content of the lookup table, we can support different matching patterns such as union, intersection, or others. We have 4 types of command. Command no push means don't push anything. It is useful for dropping unwanted elements, such as unmatched element in intersection. Command push default means push a default constant element. It is useful for inserting dummy elements, such as for unmatched elements in union. Command push current pushes the element from the input array normally. Command push most recent means duplicate the last element in the FIFO. It is useful for broadcasting for one-to-many match. Putting everything we have so far, we obtain the definition of our abstract machine. It starts with the extended merge sort for the 2 input arrays. Then, extract 5-bit info and use a lookup table to determine the commands. Following, we have a pair of controlled FIFO to take those commands. Finally, we execute the binary function in an element-wise fashion. Using this uniform framework, we can create even more fun in usage, not just the boring union or intersection. Like this, range match. The first array defines the delimiters of the ranges, and the second array defines the queries. In fact, our method can support up to 2 to the top of 128 patterns. That's a huge number. Now, let's introduce our SIMD primitives. The first SIMD primitive is KeyCombine. It corresponds to the extended merge sort and the extraction of 5-bit informations. The KeyCombine primitive has a core feature to support the keys to be tuples of arbitrary size. We can use a cascaded sequence of KeyCombine, one field at a time, starting from the most significant field to the least significant field. The second SIMD primitive is match. It looks up the table in parallel to generate commands. The third primitive is SE_permute. It emulates the controlled FIFO, but executes in parallel. The SE_permute can also support values to be tuples of arbitrary size. Just invoke the SE_permute multiple times, one field at a time, and reuse the same command control. The last primitive is related to the divide and conquer relation. With the first 3 SIMD primitives, we can already handle the problem with input shorter than SIMD_viz. But how to support a problem with longer input? The naive divide and conquer using SIMD boundary will produce incorrect result, but we found a general and correct way to do this. The last primitive, the GetBreakpoint primitive, is used to calculate the correct boundaries for the divide and conquer. Finally, we wanted to note that due to some engineering constraint and subtle issues, the primitive interface presented here is not completely the same as our implementation, but don't worry, the main idea is still the same. Now, let's talk about the circuit design. The circuit design for the KeyCombine primitive is based on Bytonic sorting network. Some changes have been made to support the key tuples. Each comparator has a 2-bit state machine for lexicographical order comparison. More significant field, if not equal, will freeze the state of comparison result. For more detail, please see the paper. This circuit is fully pipelinable when KeyCombine is used to handle a sequence of fields. The circuit design for the SE_permute is based on what we call the squeeze-expand network. We exploit the fact that we only need to support FIFO expressible permutations that reduce the hardware cost to V log V and avoid the general-purpose crossbar. The latency for each layer is 2 to 3 gates. The routing control, please see paper. The circuit for the match primitive is mainly a lookup table, that is, a bunch of muxes in parallel. It also has some post-processing that converts the commands into routing control of SE_permute. That part is mainly a prefix and a suffix scheme. For more details, please see the paper. The circuit design for the GetBreakpoint is mainly a prefix scheme followed by the last active element selection, which is used to pick out the last legal position as a breakpoint. So far, all 4 primitives are V log V cost. Now, let's move on to the experiment. We extend the GCC compiler and the Gen 5 simulator with the new SIMD instructions. The base ISA is ARM v8 with SVE extension. The array overhead for a modern 4-core CPU is less than 1000 when SIMD with V is 16. For sorted set operations and drawings, we achieved 7 times speedup. This experiment also shows our flexibility to support different types of merge patterns. This figure shows a performance for additions and element-wise multiplications between sparse vectors, matrices, and tensors on real number and complex numbers. It also includes a kernel used in shortest path. When SIMD with V is 16, we achieve 4 to 8 times speedup. It shows our flexibility to support different key value data structure and the ability to support customized binary operator. The major contributor for the speedup is the reduction of iterations in the main loop. In each iteration, the SIMD version processes 1.5 V times more tuples than the scalar version. Although the SIMD version has 3 times more instructions per iteration and slightly higher CPI, but the total effect is a net speedup. We also look at the complex workloads, where MSO is used as a basic building block and will be invoked multiple times. For sorting, we achieve 8 times speedup over the scalar sort, or 3.4 times speedup over the SIMD sort that only use the existing SIMD instructions. We can also accelerate SpGEMM, the multiplication between two sparse matrices, because SpGEMM is also dominated by weighted sum of sparse vectors, which is an MSO. In fact, when SIMD with V is 16, we achieve 4 to 5 times speedup over the base one of the scalar kernels. There are SIMD-based SpGEMM kernels in prior work, but they are implemented on x86, and there is no way for us to directly compare with them. So we use portable baseline as a bridge to perform cross-platform comparison. When running on the same dataset, prior work used SIMD to achieve a speedup by percentages, while we achieve a speedup by a factor of 4 to 5. Therefore, we believe that when the platform is normalized, we can still achieve 3 to 4 times speedup over the prior SIMD work. Let's look at what we have done so far. We observed the broad applications of MSO in scientific computing, graph, sorting, and database. We also noticed the difficulties that prevent it from being vectorized. Then, we present our solutions that include an abstract machine as a uniform representation for MSO, 4 composable SIMD primitives, and efficient circuit design for those primitives. We also performed a GenFile-based CPU simulation that shows our flexibility and good performance improvements. Finally, all source code are available online. You can also try to use the new instructions without bothering to build the modified GCC and GenFile. There is a macro-controlled switch. By unsetting the macro, the SIMD instructions will be emulated by plain C++ functions.